Hello to everyone. My name is Giuseppe Lucente and I am a PhD student from Bari University. Today, I will present this paper with title Heavy axion-like particles in core collapse supernovae, constraints and impact on the explosion mechanism. In this paper, we consider the minimal model in which heavy axion-like particles with masses of the MeV interact only with photons through this CP-preserving Lagrangian, where Ga gamma is the photon coupling with the dimension of the inverse of an energy. In this mass range, ALPs could be directly detected with beam dump experiments, and they could have cosmological and astrophysical implications. For instance, they could modify the stellar evolution, and in this way, bounds from helium-burning stars and supernovae can be obtained. In particular, in this work, bounds from supernovae will be revised and updated. So let's briefly revise the mechanism of a supernova explosion. A core collapse supernova corresponds to the terminal phase of a massive star, which becomes unstable at the end of its life. As a matter of fact, the central degenerate iron core begins to collapse because of gravity. But when the nuclear densities are reached, it becomes uncompressible and a shock wave is generated, reverting the implosion into an explosion. The major role in a supernova explosion is played by neutrinos. As a matter of fact, the 99% of the released energy is emitted by neutrinos and antineutrinos of all flavors, with typical energies of about 15 MeV in a neutrino emission which lasts about 10 seconds. Supernova neutrinos were observed for the first unit time from supernova 1987A, but although the expected galactic supernova rate is about 1-3 supernova per century, no stellar collapse has been observed since that year. And for this reason, the realization of supernova simulations has become a really important tool to study the physics of supernovae. In particular, in this work, we used a spherically symmetric supernova simulation with the progenitor mass of 18 solar masses, the same as supernova 1987A. The simulation shows that the neutrino emission can be divided into three phases. The first one is the neutronization burst, which happens as soon as the shock breaks out, and is dominated by the emission of electron neutrinos because of the deleptonization of the outer core layers. The second phase is the accretion phase, in which the shock wave stalls and the neutrino production is powered by the unfolding material in the interior of the star. In this phase, part of the neutrino energy is deposited behind the shock in order to revive it. The third phase is the cooling phase, in which the supernova can be roughly seen as a black body cooling via the thermal emission of neutrinos and antineutrinos of all flavors from the so-called neutrino sphere, which is the neutrino last scattering surface. Now, the supernova explosion is strictly connected to the time evolution of three characteristic radii of a supernova atmosphere. The first one is the neutrino sphere radius at which neutrinos are supposed to be thermally emitted. The second one is the gain radius, beyond which the neutrino absorption is larger than the neutrino emission. It is of the order of 100 kilometers during the accretion phase, but after the explosion is definitely triggered, it decreases and becomes of the order of 25 kilometers at 1 second after the core bounce. The third radius is the shock radius, which represents the position of the shock wave front. In particular, the region between the gain radius and the shock radius is the so-called gain layer, where the neutrino heating useful to revive the shock is efficient during the accretion phase. So this is the unperturbed supernova model. In this context, ALPs could be produced through two production channels. The first one is the Primakoff effect, which is the conversion of a photon into an axion of the same energy in the electric field of free protons in the supernova core. The ALP volume production rate for this process is proportional to the square of the coupling constant, to the temperature T, which is of the order of 30-40 MeV in the supernova core, and to the screening scale Ks, which accounts for the finite range of the electric field in the stellar plasma. In particular, it is proportional to the effective number density of free protons in the supernova core, which takes into account for the partial proton degeneration through a polyblocking factor. The second production channel is the photon coalescence, which is the production of an axion after the annihilation of two photons in a medium of sufficiently high density. In this case, the production rate is proportional to the square of the coupling constant, to the Boltzmann factor, and strictly dependent on the axion and photon masses. In particular, it has a kinematic threshold, vanishing for the axion mass lower than twice the photon mass, where the photon mass is essentially given by the plasma frequency, which is of the order of 10 MeV in the supernova core. Now, from the axion production rate, one can compute the ALP emissivity, which is the energy emitted per unit volume and time by ALPs. By integrating it over the supernova model, one can obtain the ALP luminosity, which is the energy emitted per unit time by ALP production. In particular, in this plot, the ALP luminosity as a function of the axion mass at 1 second after the core bounce is shown for the Primakoff process and the photon coalescence. In the small mass limit, the photon coalescence is negligible, but it becomes dominant at masses larger than 80 MeV before being Boltzmann suppressed. So the total ALP luminosity, which is the sum of the two contributions, is essentially given by the Primakoff process in the small mass limit and by the photon coalescence at larger masses. At this point, we can compute the axion bounds. As we know, if novel and weakly interacting particles are produced in supernova core, there will be free stream. And so the total energy emitted in neutrinos would be reduced, and the duration of the neutrino burst would be shortened. Assuming that the supernova 1987A neutrino burst was not shortened by more than 1/2, leads to the approximate condition that the ALP luminosity should be lower than the neutrino one at 1 second after the core bounce. This is the so-called energy loss argument. In particular, our constraining strategy, dubbed the modified luminosity criterion, is based on the assumption that only the ALP energy which cannot be reprocessed efficiently as neutrino 1 is relevant for constraining the ALP parameter space. More precisely, if ALPs are produced behind the neutrino sphere, they will steal energy from there. However, if they are reabsorbed in a region where the neutrino production is still efficient, their energy would be reconverted into neutrinos, and so the neutrino signal would result to be practically not altered. On the other hand, if they reach a radius beyond which the neutrino production is negligible, and this radius is assumed to be the gain radius, their energy will result to be no more available to neutrinos. For this reason, in order to take into account this effect, the ALP luminosity has been modified by including an optical depth factor characterizing the probability that an ALP produced behind the neutrino sphere reaches the gain radius. In particular, the optical depth is obtained after an integration over the supernova model of the inverse mean-free path, which is determined by two absorption processes, the inverse Primakoff and the axion decay into two photons, and results to be proportional to the square of the coupling constant. Now, when the ALP photon coupling is of the order of 10 to -9 inverse GeV, will free stream as soon as they are produced in the supernova core. This means that their mean-free path is much longer than the gain radius, and so their optical depth factor tends to 1, and the modified luminosity reduces to its standard definition, which takes into account only the ALP production. The red region shown in this plot has been excluded through the energy loss argument in the free streaming regime. In particular, in the small mass limit, where the coalescence is negligible, we reproduced the same results obtained in previous literature works, which considered only the Primakoff process. On the other hand, at larger masses, the previous bound has been strengthened by a factor of 3 at 100 MeV and by more than 1 order of magnitude at masses larger than 200 MeV. However, as the coupling constant increases, ALPs will be trapped in supernova core, since the mean-free path becomes of the order of the core radius, which is about 10 kilometers. In this context, the modified luminosity is suppressed by the optical depth factor. So as shown in this plot, at fixed axion mass, there are two critical values of the axion couplings, and all the values between them are excluded since the ALP luminosity is larger than the neutrino one at 1 second after the core bounce. In particular, for couplings smaller than the lower one, ALPs are so weakly coupled that they are produced not sufficiently to modify the explosion of the supernova. On the other hand, at couplings larger than the higher one, ALPs are so strongly coupled that they cannot reach the gain radius, and so the neutrino signal is not modified. So, to summarize, in this plot, it's shown an overview of the AV-ALP parameter space. In particular, our new bound is this purple region, and it has a nose-like shape since the photon coalescence has been considered. It's really interesting to stress that the combination of bounds from supernova, beam dump experiments, and HB stars, which we recently computed in this paper, leaves open a small triangularly shaped region at masses of 0.5 or 1 MeV and couplings of the order of 10 to minus 5 inverse GeV. And this is the so-called cosmological triangle, which is called in this way because only standard cosmological argument could close it. However, it could be really interesting if some new experimental results could close this window. At this point, let's evaluate the possible impact of AV-ALPs on the supernova explosion. Actually, we know that after the core bounce, a shock wave forms within the iron core, but then it dissipates its energy because of the dissociation of the AV nuclei in the outer layers of the star. Therefore, in about 200 milliseconds, the shock wave stalls and starts to recede. In the so-called neutrino-driven explosion scenario, the shock wave is revived by neutrino heating, enhanced by convective processes and hydrodynamic instabilities. In particular, neutrinos revive the shock since they deposit energy behind it via charge current interactions with the free nucleons in the gain layer. However, there is no proof that this mechanism is really robust, and in spherical symmetry, explosions typically fail. In this context, ALPs decaying into photons may provide an efficient energy deposition behind the shock, since photons quickly thermalize with matter. An interesting starting point to assess this possibility is to verify if the energy deposited by ALPs in the gain layer competes with the neutrino heating when the shock recedes at about 200 milliseconds after the core bounce. In particular, in this isocontour plot, it's shown how the ALP energy deposition rate in the gain layer varies with the axion mass and coupling at 200 milliseconds after the core bounce. The white region is excluded through the energy loss argument. The blue region, the energy deposited would be too low, while something interesting could happen in the orange region over the dashed line, since in this region, the ALP heating is comparable to the neutrino one in the gain layer. So in order to do a numerical example, let's fix the value of the axion mass and coupling and evaluate the energy deposited by ALPs and neutrinos in the gain layer. It is apparent that at early times, the axion contribution is negligible, but it increases with time. In particular, at 300 milliseconds after the core bounce, when the explosion is definitely triggered, the energy deposited by ALPs is of the order of 10 to 51 erg, and this would be sufficient to partially melt nuclei. For this reason, the explosion could be helped in this way. So, now to conclude, since in the supernova core the temperature is of the order of 30-40 MeV, one can explore the parameter space of ALPs with masses of 100 MeV or more. Through the energy loss argument, one can put a stringent constraint on the ALP photon coupling, and for masses larger than 100 MeV, the previous bound has been strengthened by considering a new production channel, the photon coalescence. Moreover, we have shown that ALPs may provide an efficient energy deposition behind the shock. So, could they be the yet missing piece of the puzzle to boost the supernova explosion energy? In order to answer this question, a self-consistent inclusion of ALPs in supernova simulation is needed, and this project is going to be developed in the next future. So, thanks for the attention.